name is Dustin Martin. I'm an MAE 535 Design of Electromechanical Systems under the instruction of Dr. Gregory Buckner. This is at North Carolina State University. For the demo project today, I'm going to demonstrate Faraday's law using a linear variable differential transformer, or an LVDT for short. What an LVDT does is it allows us the means to measure linear displacement over a distance without any sort of mechanical interface of components themselves. So let's take a quick look at a demonstration here to show exactly what we're looking at.
An LVDT typically consists of an iron core moving relative to an outer cylinder which houses a primary coil and two secondary coils. The primary coil is being driven by an alternating current which induces a magnetic field on the iron core, which is similarly alternating, and therefore, per Faraday's law, would induce currents on secondary coil 1 and 2. Depending on the number of turns linked between the secondary coils and the primary coil and the iron core, the voltage signal will change between them. As the iron core moves, the flux linkage between the primary coils and the secondary coils changes. In the far right position, the secondary 2 to primary coil flux linkage is much greater than that of secondary 1 to primary, and therefore its output signal is much larger. However, if we move back to the null position, the flux linkage between secondary 1 in the primary and secondary 2 in the primary is equal, and therefore we have inverse sine waves of equal magnitude. If we've moved back to the left, however, the secondary 1 to primary is much greater than that of secondary 2. We can then add these two signals together, and it gives us the ability to see as we move the iron core from left to right, the secondary 1 plus secondary 2 output signal on the bottom changes, and therefore we can convert this signal into a displacement and determine what the relative motion is between the iron core and the outer tube cylinder.
So in this particular demonstration, I'm actually going to use two separate straws, one larger external straw and an internal straw in the center of those. I wrapped this inner straw with approximately 12 feet of 30 AWG magnet wire. That's being driven by approximately 300 kilohertz sine wave from a signal generator. These two secondary coils are going to reside on the outside straw itself, and they're hooked to my oscilloscope. So as I pass this inner straw into the middle and apply a flux linkage between the primary coil being driven by the signal generator and our two secondary external straws, I actually generate a signal on the oscilloscope itself. Right now I'm approximately in the null position based on the indications on my diagram here. And what that means is that the flux linkage between the primary coil and both secondary coils is approximately the same. On this oscilloscope, I actually have the inverse function here, which gives us the ability then to add them two together. And it gives us just a slight signal, but it's essentially zero in this particular case. Now, as I move the position of the primary coil left, the flux linkage to the left coil actually changes, and it allows me to get a signal on my oscilloscope. So I can measure that voltage then and provide a calibration curve, and that will tell me exactly what the position of this outer or inner straw is. Now if I look at that back on a dual channel, you'll see that I lost basically all of my coupling with the right coil itself, but I still have plenty of coupling on the left coil. Now conversely, as I move it back to the right, I start to get a erroneous signal, but I lose essentially all of my coupling with the left coil, and I'm generating a signal on my right coil. So then if I add those back together, I have voltage signal on my right, and I can measure that. And as I move it back to the null position, we'll see that we get our signal back, and that we jump back to approximately 0 volts. And then back to the left and to the right. With that, we can put a calibration curve together, and we can apply this to a displacement, the inner cylinder itself or the external, whichever one you would prefer to attach for the relative motion itself. But we can then determine exactly what the distance traveled is in a very linear fashion. Action. Now, should you have any additional comments or questions on LVDTs, please feel free to get in touch with me via email. Thanks.